Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Welcome to the Ex Terra Podcast. I'm Tom Patton. The next 2 weeks on the Ex Terra Podcasts, we're going to take a look back at some of the most viewed episodes from the past year. It's been an exciting year in space commerce, and we've chatted with some very innovative companies that are doing some very interesting things across all verticals in the industry. And let's start out with space domain awareness, which has been a much discussed topic through 2024. The 27th edition of the Novaspace Satellites to be Built and Launched report forecasted an average of over 3,700 satellites will be launched annually between 2024 and 2033. That's equivalent to about 10 satellites per day. And keeping track of all those satellites, not to mention all of the accumulated space debris in low, medium, and geostationary Earth orbit, is only going to get more complex. Scout Space launched its first in-space products and services in 2021, allowing spacecraft to see and understand the things around them while on orbit. We caught up with Philip Hoover-Smoot, the CEO of Scout Space, who explained the different types of scenarios encountered on orbit.
Every single mission is a little bit different. So it's always very hard to talk in generalities for space domain awareness. But when we conceptualize what the autonomy customers are going to be looking for, that comes down. There's probably two good illustrative examples that I can give that kind of show either end of the spectrum here. One would be your classical constellation operator, right? That is out there flying a number of satellites in some preset configuration through congested space. By enabling that and empowering that constellation with a vision plus autonomy capability, i.e. something more than just hey, there's a conjunction that might happen, you might want to take a look at it, but really to say, hey, look, this conjunction might happen because the object that's coming close to you is uncatalogued. And that bolt that flew off the thing that's never been in a catalog is about to hit you. You don't have time to get that data from the ground. Frankly, you can't get it from the ground anyways because the sensors aren't sensitive enough. Can't see it with optical from the ground because they're not sensitive enough. Right. But it's still going to hit you. What do? You have to have the ability to find the object, understand if the object actually poses a threat, and react. So in our mind, if you're flying a constellation, you've invested quite a bit of money into it. You want to protect it. You want to have the ability to know that, despite, yes, you can go pay the Leo Labses of the world a monthly fee to go get conjunction assessments, but there are still other things out there that they can't see that are a threat to the product. We want to enable those operators in the near term, right? And I'm talking about kind of the next couple of years to find, understand, and maneuver around those uncatalogued or cataloged but not accurately tracked objects. That would be a small maneuver, right? So when you think about autonomy, we also think about this in a decision-making framework being the be-all and end-all of this, as opposed to kind of traditional autonomy when we think about self-driving cars. So let me unpack that a little bit, right? So if you're designing a car to go be a self-driving vehicle, your problems are the problems we all know they have, right? They occasionally slam into a cyclist, or a grandma crossing the street looks like a tree, and suddenly the software doesn't recognize it as a person, and there's a problem. So that is not necessarily our problem on orbit, right? On orbit, you've got 6 degrees of freedom. Arguably, you can probably move a kilometer in any direction. You're not going to hit much, right? Space is big. The problem is, how do you get trusted data to allow you to make a decision? Once you've made the decision to maneuver, the actual maneuver is pretty straightforward. So we kind of think of autonomy as decision-making. It's not really the actual maneuver part. Frankly, you just turn the propellant on and make sure you're pointing the right direction and move, right? Cool. We'll leave that to other people. We want to make sure that we're providing accurate federated learning capabilities that allow someone to take inputs either from our sensor or other sensors from satellite systems and to make a decision that can be trusted to allow for that small maneuver. And that is how we think about autonomy. Additionally, the kind of flip side of that, so we talked about kind of that was macro constellation level, how to protect your assets. The other side of autonomy, of course, is the classical servicing economy opportunity. And I came from 2 different OTV companies. momentous in spaceflight. We built, the Vigoride and the Sherpas, some of the earliest OTVs. And I've seen firsthand the struggle of trying to understand how these missions can actually be licensed and operated, right? And the idea is sound. The opportunity is sound. But the problem is it's far more complex to go off and go actually safely approach and grapple with an object than you might actually think, right? And if you look at any of the federal government's regulators' reviews of these applications, there are a lot of questions being asked about, hey, how do we know that your algorithm's the right algorithm to do safe standoff and approach, right? So as you're getting closer to things on orbit, of course, the risk of collision goes up, and you don't always have the ability to communicate, right? Like, we don't have functional mesh networks on orbit. Most of these early stage companies don't necessarily have real-time communications. Not that that actually really exists for most people, but really they're talking to their satellite every once in a while, right? And the passes are not totally consistent. So when you're getting really close to an object, you have to have a level of autonomy baked into that capability, because you're not always going to be in communication with your satellite. So it has to be able to understand its environment, make decisions on it, and make decisions that are trustable to the point that you can get a very expensive satellite close to another very expensive satellite and make sure they don't hit and create debris. We think that there's a good, standardized, trusted set of autonomy algorithmic capabilities that can be developed that we think will be eventually approved very easily by regulators, that we want to make the industry standard. We don't think it's wise or advisable for the US government or other allied governments to be licensing spacecraft as one-off snowflakes and unicorns every time, right? Sure. A new algorithm every time. That's going to create risk, and risk is going to eventually create a problem. And we frankly can't accept problems at the scale of what those problems might be. So if we want the orbital servicing economy to be what we all want it to be, we have to be able to develop both trusted data about where objects are in relationship to each other over time without losing track, and then make decisions on it in a way that is safe and trustworthy, which again means federated learning. So that's taking a bunch of inputs from a bunch of different sensors and sources and making sense out of it in real time without a human in the loop. So that's really what we're going for on the autonomy front.
Hoover-Smoot also talked about the project Scout Space is working on with Dawn Aerospace to put sensors aboard the Mark II Aurora spaceplane in very low Earth orbit.
If you're in LEO and you're looking down into VLEO, more likely than not, some exceptions about, maybe you can catch something kind of like around the edge of the Earth and the land, or whatever, but more likely than not, you're looking at an object that is scattered with Earth light, right? Sure. So you're actually going to struggle to do a lot of the processing and kind of, data value additive things that you need to do to have meaningful SDA instead of just like, oh, there's an object right there, right? That's less useful than making it actionable intelligence out of it. So you want to be able to have a clean image. Well, as I said, you can't really do it from the ground all that well because your opportunities are limited. You can't really do it from above because you're looking down, you're going to have all this backscatter and backlight. So it's like, well, how can you just get higher, right? And fundamentally, the Dawn Mark II suborbital craft is just a really interesting demonstrator opportunity for us to go and look at what it would take to put sensors in the fuselage of the aircraft, cut out the top of the fuselage, put in a kind of a proprietary optical window, and then mount a number of sensors inside. So we're flying 2 different cameras, actually probably 3 different cameras of 2 different types on our concept of operations or our kind of demonstration mission to go off and go think about what this would be. And we think there's a really interesting niche there, not just because VLEO is an emerging kind of threat environment, not just because Russia and China are actively putting things up in VLEO, most of the time observation platforms, because of obvious reasons. It's easier to see things when you're closer. But because there's no other solutions out there. There isn't another solution. And moreover, these solutions that are out there are extremely expensive. VLEOs, you got to go to LEO first and then work your way down. So you need effective prop. By the time you get there, you have to have a very effective prop system and a lot of prop itself to go off and go persist there. Otherwise, you just get dragged back to the Earth. So it's a hard operating environment. By using a reusable, taskable, fly from anywhere platform, we don't have to build an expensive spacecraft with a capable propellant system and launch it and then deorbit it. Like we can literally throw one of these in the back of a C-17, fly it to an atoll anywhere in the middle of the, pick an ocean, and we're on orbit a couple hours later. The mission profiles are short, right? It's 45 minutes. Right. Wait for the thing to fly over. You fly up, you take some pictures, you land. I get my sensor back. Dawn gets their airplane back. It's a classic reusability thing, right? Otherwise, anything you fly up into VLEO is going to burn the hell up. My sensors don't burn up, I get it back, right? So I only need to build a couple of these things. So the economics, the price point is just really, truly phenomenal. So in my mind, this is a really elegant solution because not only am I solving a problem that's uniquely difficult for SDA operators in VLEO, but I'm also doing it in a way that arguably is going to be like factors cheaper and dynamically possible. You throw something in VLEO, you're in one plane in one place, right? Yes, you can maneuver around. That gets very expensive and time consuming. I can build and I can put 3 of these things on 3 continents and fly them, and the price point is a tiny fraction of what one satellite in VLEO would actually look like. And I can be right up close and personal with these things in the future on kind of future variants of this that you just can't ever possibly achieve it anywhere near the same price point. So solving a problem that's an emergent problem that people really very much do care about. And I'm doing it at a price point by leveraging reusability that no one can touch. It's just an absolutely beautiful solution.
Philip Hoover-Smoot is the CEO of Scout Space. Well, getting into space is very loud. There's no way around it. The controlled explosion that propels a spacecraft into orbit generates a lot of noise. Anyone who's ever watched a launch in person knows how true that is. But sound can have a very detrimental effect on the spacecraft riding on the rocket. Sound is nothing more than a vibration, after all, and shaking things often leads to breaking things. That's why acoustic testing is such an important part of evaluating a spacecraft's fitness for flight. MSI-DFAT is a company specializing in acoustic testing for spacecraft and the components that will fly to space. And I had a chance to talk with several representatives of the company, including Allesandro Carrella, Vice President for Strategy and Growth, who explained what their testing regimen involves. You all mentioned a couple of times vibration testing, and I think it might be helpful to have folks understand the difference between acoustic testing, which basically shakes things, and vibration testing, which basically shakes things.
Exactly. We call it vibroacoustic testing. In fact, we call it vibroacoustic, and then we cover both. We cover. I think the difference is so if you look at this, there is an interesting chart that I usually use during my talks, and there is a frequency range difference. So there is vibe testing is structural borne vibration. So the spacecraft is on an adapter which is in the fairing, and so there's a lot of vibration coming through the base, and so there's a lot of base testing, base vibration, and there is, for example, ignition and all the initial part of the engine liftoff are covered by a sine test. So there's a sine sweep test that goes between 5 to 150 hertz, and then after that there is under 20 hertz, and then there is a random vibration test, so it goes all the way to 2 kilohertz, and then there's the acoustic test that covers up to 10 kilohertz, and then there is a pyroshock which covers up to 100 kilohertz. So that is so the different tests cover different ranges of the live the harsh condition at launch, all the way to shocks. The shocks, the pyroshocks. So there's a lot of pyrobolts, a lot of mechanism. Every time that a booster gets separated, when the spacecraft is released, there's a lot of shocks, and so G's that can reach in the thousands of G's. Up to 100 kilohertz. So those are different tests. So there are different tests for different frequency range and different part of the launch, and acoustic is one of them.
Bradley Hope is the U.S. sales manager for the company.
We're essentially recreating the very harsh noise and vibration environment created by sound during rocket launch. That's a very violent environment, and it's part of an overall series of tests that they call environmental tests that a spacecraft will go through prior to launch. So typically you'll go through different types of vibration testing where you mount mechanical components or assemblies on shaker tables and shake it. You'll put it in an oven and bake it. And usually around the last one in a series is the acoustic test. So the jet engines or the rocket engines emit a very loud sound. I think the SLS was somewhere around 200 decibels, if I remember correctly, of the external noise environment. So if you look at any rocket launch, one thing that you'll notice is often there's big pools of water underneath the launch pad, and that collects and absorbs a lot of the sound energy. So that sound energy is not all captured by that pool of water, but helps dampen down some of that response. The rest of it, as it launches, there's several different environments that it goes through, and that acoustic energy vibrates up into the structures. So the sound or the airborne acoustics translates into structural based vibrations and can affect and break and damage different parts of the rocket. So the environment that we are recreating most typically is the one that's inside of the fairing. So all the external noise comes into the fairing. There's some lessening of the amount of acoustic energy, so that 200 or so decibels outside of the rocket turns into about 150 inside the fairing. And just to give people a little bit of a reference scale, I think a lawnmower is around 80 decibels, a rock concert's around 100 decibels, and then you start popping eardrums around 130, and 150 is fatal to humans. So your organs and parts of your body would resonate until it would become fatal to you. So it's a very, very violent noise environment. There's other applications that we do besides just recreating the fairing, but 90% of the business is testing a satellite or a space telescope or the fairing itself or any part of a rocket or payload that's getting launched into space.
Coming up, software-defined satellites and the role of AI in space domain awareness as we take a look back at 2024 on this edition of the Ex Terra Podcast. But right now, take a moment to click subscribe to be sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. Well, since their inception, most satellites have been defined by their hardware. They were built for a specific purpose, and that's what they could do. Now there's a growing trend towards software-defined satellites like the ones being built by ReOrbit. Sethu Saveda Suvanam is the founder of ReOrbit. I started out asking him how a software-defined satellite differs from a more traditional satellite.
So if you traditionally look at how satellite industry has been, working way since Sputnik, the first satellite, has been launched, it's been very much hardware oriented, right? Like whenever you're designing a satellite, you start with a mechanical form factor, then you put all your subsystems, into this box, and then the last thing you do is actually you're writing your flight software, your application software, and so on and so forth. But if you keenly follow technological evolution of, let's say, industries that are very similar to satellites, for instance, automotive, computers, mobile, even the fighter jets today, they all started in the same manner, very hardware oriented. But now the core of innovation in these industries come from software, right? Like today, if you buy Tesla, you're not actually buying Tesla because of its hardware, probably some do, but the core value of Tesla is actually the software nature of what it brings. Similarly, the fighter jets today, largely all the fighter jets are software defined, and the mobiles and computers today, when you buy an Dell or a Lenovo computer and open the hood, none of the hardware inside is actually very similar, but they all run similar softwares, which is Windows or the operating systems. So what we do is we are trying to bring similar innovation in the space industry. So instead of starting with mechanical form factors and hardware, we start with software. So we have now developed a stack of software as a backbone to our system architecture. And this is fully developed and de-risked through an ESA program. And then we treat hardware as a commodity. Probably we are the only one space company where we sell satellites, but we don't manufacture any hardware in-house. Whenever we get a customer, we go to the market, buy the best-in-class hardware with a lot of heritage that suits the requirement of a customer. Then we gel all these hardware around our software. The only, let's say, customization we do is like we develop the drivers between the hardware and the software that we have so that they're compatible to stick around our software. And then the system is ready to go. By this way, we bring a lot of flexibility, a lot of cost reduction. But also what we can do is we can actually start developing a lot of advanced functionalities on top of our software framework way before you have your hardware. For instance, our satellites are designed like a flying router. So you launch one, you launch another, all the software protocols that are required to exchange data, exchange information comes inbuilt.
Suvanam said that the software-defined approach provides a lot more flexibility to satellite operators to get more utility out of their spacecraft.
So when you want to build, for instance, applications such as rendezvous, proximity, docking, or in-orbit data transfers, these are all driven by software but they have a strong connection to hardware. But when you're starting as a hardware first, with hardware first approach, you cannot actually start developing the software unless you lock your hardware. And today, some of these applications, you don't have the hardware to actually do these kind of applications. So you're sort of locked by the limitations of the hardware. Whereas if you're starting the other way around, you could always start developing all these applications on top of your software stack or your software framework. And then when and then the hardware comes, you could sort of tailor your hardware to suit these kind of requirements. So you could always be one step ahead of the industry by going this way. And the big, I would say, one of the disadvantages, I would say personally from how I see it is educating the industry more than anything, because space industry is very conservative, as you know, probably, Tom. And probably it's more conservative than the construction industry and some of the other traditional industries. So in that sense, really, when you're coming with an idea that's drastically different from what people have been used to in the last 60 years, so going to one suppliers and basically saying, look, you don't have to worry because we take all the stuff on our side when it comes to adopting to your hardware, but also going to the customers and saying, look, this is the advantage you get. It requires some convincing. And once you sort of pass that line, I think this is the way the industry will go. And I said, again, if you draw parallels, any industry you see today that's accelerating at an enormous growth rate, it's because of software first approach. It's not because you're locked by hardware. And I'm pretty sure in the next 5 years, satellites and space industry will follow this, software-enabled architectures.
Are you finding, though, that the satellite manufacturers are protective of their proprietary software? Do they not want you to take one of their pieces of hardware and say, okay, I'm going to rewrite and completely change the way that it works?
Yes. I mean, if we buy it from, let's say that used to be the scenario 10, 15 years ago where the number of vendors have been very limited. Whereas today, if you took, if you take the number of vendors at every subsystem level, it's a huge, huge industry, right? Like let's take propulsion. Just France, Germany, UK has maybe more than 20, 30 propulsion companies, or probably even more if my number is wrong. So, and then you could sort of boil that down to every subsystem. Just, in Europe, you have probably 50 to 20 to 50 subsystem vendors for every subsystem, so, who are purely only focusing on that subsystem, right? And that's where I think this is again a testimony to the industry moving into the right direction, because once you have an industry where a lot of these subsystem providers are coming, tier 2, tier 3 suppliers are coming, it basically means that hardware is almost becoming a commodity. And now, you need to bring innovation on the more system architecture level, which is what we are trying to bring. So for us, it becomes much more easier today to actually go to these suppliers, tier 2, tier 3 suppliers, where we can say, look, you don't have to worry, we'll just adopt. And they're actually happy because this also helps their business in a way. If you as a satellite manufacturer are not bothered about manufacturing hardware, it actually brings more business to these subsystem vendors. So they're actually very happy to collaborate with us and take this kind of architectures forward.
Sethu Saveda Suvanam is the founder of ReOrbit. And finally, one of the biggest buzzwords for 2024 has been AI, or artificial intelligence. And one of the tasks that AI seems to be particularly well suited for is space domain awareness, keeping track of as many of the objects in orbit as possible. Slingshot Aerospace is a company providing satellite tracking, space traffic coordination, and space modeling and simulation solutions to a variety of clients, and they're at the forefront of developing AI models to assist in space domain awareness. I talked with Dylan Kessler, VP of AI and Data Science at Slingshot Aerospace, about some of those advancements. He explained how AI is playing a role in space domain awareness.
Space situational awareness, space domain awareness, it's complicated. There's a lot of information, a lot of data streams that are out there. There is a growing number of objects that are out there. Slingshot has developed the DARPA AI system, which is one of our solutions for the government to help with space domain awareness. We worked with DARPA on a project. We announced that in June, that the system was intended to detect anomalous satellites. And that might sound like something that we could do with computers before, that might have been simple before. But the challenge was that we're seeing new constellations of satellites go up, multiple constellations of 10,000 or more satellites go up by the United States, but also by international partners and competitors, and that potentially some of the satellites hidden within those constellations could have nefarious motives. They could be carrying hidden payloads and literally acting as if they're one of those satellites in those constellations. The amount of data associated with those constellations, if we're observing them with sensors, is huge. And historically, we might have had people evaluating those data. How bright are all the satellites? Are they maneuvering the way we would expect? Is one of them different from the other? But when we start to talk about tens of thousands of satellites that are doing much more in space than they have before, the amount of information becomes overwhelming, not just for one person, but for all the people we could throw at it. So AI does a great job of taking many data streams and sifting through those and building representations that are useful for people to think about. The Agatha system does exactly that. It has the ability to look at many data streams, whatever we throw at it, and it will evaluate and identify sets of objects that should be cooperating. And if there's one of them that seems to be a little different, it'll flag that for further investigation. So in general, there's sort of a scaling aspect to it. I think there's also a behavior aspect to it.
Okay.
Yeah.
Well, and I didn't mean to cut you off, but when you talk about an anomalous satellite, are you talking about something that if let's say unfriendly government was putting up a constellation of satellites, they might put one up there that looks like it's part of the constellation, but has a different function. And then the other thing is that could somebody put a satellite up into a commercial constellation that doesn't belong there, but it's really tough to detect? Is that the kind of thing you're talking about with an anomalous satellite?
Sure. So you can imagine you can hide something by making it invisible, or you can hide something by hiding it in the open and making it look like everybody else.
Sure.
And that cryptic satellite could be carrying jamming equipment. It could be carrying, it could be carrying what other sorts of things that we've seen in the press, and maybe pretending like it is one of the satellites that is, say, a communications satellite, or it's relaying information for the public or internet or whatever, but really it might have an ulterior motive.
Slingshot is also working with NOAA to develop the presentation layer for its track system. Kessler said AI will be a key component in keeping track of what's in space.
It's also one of those situations where we have more and more information that's coming around right now from all of these sensors. We recently published a paper at the AMOS conference, the Advanced Maui Optical Space Surveillance and Technology Conference, where my team put together both machine learning and AI techniques and the physics-based astrodynamics techniques that would have been looked at for conjunction analysis. And we found that the inclusion of AI and the inclusion of machine learning into that process of evaluating space traffic helped us identify conjunctions, potential collisions that were coming that would benefit from additional sensor tasking. So we could gather a little bit more information on those and improve safety by really focusing on the dangerous ones with the limited sensor resources that we have. I think there's lots of other situations where we have tons of data coming down for traffic coordination, and AI is going to be a piece of that.
Dylan Kessler is VP of AI and Data Sciences at Slingshot Aerospace. Well, that's going to wrap up part 1 of our look back at 2024 on the Ex Terra podcast. Next week, we'll revisit 3 more of the most popular podcasts of the year and give you a quick look ahead at what we're planning for 2025. As always, be sure to check out our YouTube channel and click on subscribe so you can stay up to date on developments in space commerce and be notified when we post new videos. You can get daily updates on space commerce by subscribing to the Journal of Space Commerce on Substack at www.xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on X at XTerraJSC. Until next time, I'm Tom Patton. Thanks for joining us.